Hi, I'm Jarwin. In this tutorial, we're going to cover an introduction to the simulator, simulator outputs, as well as we will look at one of the my simulated circuit as an example. So, how the simulator works. Flux as one of the world's first programmable simulator. That means that you can actually write and publish your own simulation model to the community library. So instead of having to hunt down those models from various manufacturers and sources, you can stand on the shoulder of others. All models are on the same platform and compatible with the same simulator. When creating a simulated circuit, just make sure that you're using part that have simulation model. So you can tell if a part as a model by the icon here, the simulation model, or by its internal, circuit. There's actually two ways to determine the function of a part, either by a code or by its internal circuit. We're going to discuss that one later on. So let's open up this fixed resistor and let's take a look at its model. So I'm going to right click and open that one. To display the simulation model of this fixed resistor, just click on the code here on top. And here, as you can see, it's fairly easy to understand. It's written in TypeScript, and if you're familiar with programming, we have also a ton of documentation if you're interested in writing your own models or modifying ang existing models by forking apart. As I mentioned, the other way a part can function is through its internal schematic diagram. In this example, you can see that I have a low noise amplifier here on my canvas, and it's a part, right? But if I click on this, if I'm going to click and open this part to view its internal schematic, just right click and select open, which I already did here. And as you can see, this is the internal schematic diagram of that low noise amplifier. It's terminated with 3 terminals, as you can see here. Signal in and RF out plus DC, that's the bias DC, and here ground. If we go back to the previous document, as you can see, that's the 3 pins for that part. Signal in, DC, RF out plus DC, and ground. Let's open one of my circuit here, the AC to DC converter, to see the simulator in action. Yeah, I know what you're thinking. That's not the AC-DC band. So let's open the AC-DC converter circuit in here, and let's just wait for a couple of seconds for this project to load. So what we're looking at now is a simple AC to DC converter circuit. The source that we have here is just a sine wave generator set at 60 Hertz and 12 volts peak to peak. No phase offset and no DC offset, just your ordinary wave generator. Attached to it are 4 rectifier diode on a bridge mode configuration plus a 1000 microfarad polarized capacitor. On the load side, we just connected a light emitting diode and a 500 ohms resistor. This is just for us to verify that we actually have a direct current on the output. As you can see, the moment I open this document, the simulator has started right away. This is because the simulator in Flux is always active. It's always on. To display the output of a part on the canvas, simply click on the part on the canvas, and on the inspector, look for the state panel. From here, you can see that we have a couple of outputs that we can enable or disable. If you want to display the output, for example, the voltage on the anode side, just click on this icon. and it will be added up onto the canvas. Same way, if we want to disable an output, click on the eye icon again to disable it. You can also move the simulator output display somewhere else on your canvas. Just drag the designator block somewhere else. Let's say, for example, this LED, this resistor load, and probably this capacitor here. And as you can see, I could see them in a row form, or I could put them stacked in top of each other for me to easily compare their output. To adjust the simulation speed of your circuit, click on the empty part of your canvas, and on the inspector, look for the simulation panel. As you can see here, I could adjust the time per step size as well as the unit and the simulation speed. But for now, I'm just using 500 microsecond step size at the very lowest simulation speed. Now, let's take a deeper look at how to write a simulation model for an operational amplifier, or commonly known as op-amp. I created a very simple circuit here, which, by the way, it's not simulated yet. I mean, on the output, because the op-amp doesn't have any simulation model yet. So we are going to write a model for it based from the documentation available at docs.flux.ai. So you can see here, the R2 doesn't have any output or current yet. It's because it relies on the output of the output side of the operational amplifier. So let's take a look at the docs.flux.ai, the documentation about the operational amplifier, and we can see here, this is the example TypeScript code or the model for an op-amp. So we need to call out the type to be op-amp, and I think we can also control the gain, the max voltage, the minimum voltage, as well as we need to also to declare some constant, the terminal UID for each of the terminal. So here, I'm going to write a simulation model for this op-amp here, which I already open in here on another browser tab here. And this is the in input 1, input 2, and then the output. It corresponds to the terminals of the part here. So from here, to start writing a simulation code for this op-amp, you need to go to the code tab here. And as you can see, I already started the template here, which let's start with the declaration of the constant. So as you can see here, the input terminal 1, which I commented here, that's the in 1, which is this terminal. And then next would be like N2, which is this one. The other one out, I intentionally made this one blank for me to show to you guys how to get the UID of a terminal. So go back to the schematic diagram and click on the terminal that you want to get the UID. And then on your keyboard, copy Command C or Control C, and then go to this website here, JSON formatter, and just paste it here. Just paste. It's a bunch of code, but it will reformat the code for it to be like very easy to read. So let's process that one. And as you can see here, these are the formatted version of the code. I mean, the whatever you copied on the terminal. So what we need to look at here is the UID. So let's take a look. Where's that UID here? maybe somewhere the bottom here. Yeah, I already found it. So here, UID, and this is the value. So we need to copy that one, copy, and then go back to here on the code, and we need to paste that one in here. So that's it. That's how you declare a constant for a terminal. So we already completed that step. The second constant here is the output voltage that we need to use during the calculation event. Let's go to the next part of the code in here for the op-amp simulation model. So after declaring all of the constant here, the next thing will be like to set up an event. So I'm just going to paste something here. So I call this one a setup event. So this section of the code will fire up as soon as you load a document or a circuit, or if this op-amp is being used as an instant to someone else's document. So as you can see here, there are a couple of constant before calling out the simulation model. So first one here is like the minimum output, maximum output, and then the gain. So these constant are just actually looking for the value of the property that has a name minimum output. If there's no value, set the default to negative 15. So it's looking for the property with the name minimum output. As you can see here on the right side, I actually added up couple of properties. So minimum output, maximum output, and then the gain. We need to make sure that the name here corresponds to the string that we are using here. So as you can see, it's identical, minimum, maximum, and then the gain. So that way, our simulation model will be flexible. So once the simulator runs, it will use the value that is like available here to replace whatever we are going to use in here. So if we look at again uh, on the op-amp example here, these are an example of a very basic hard-coded value. This one is like if you every time you need to change something, maybe the gain, you need to go inside the code and then change the gain to maybe like 50,000 k, 50k, 10k, something like that. But in here, because we are using the properties feature, so every time you change this minimum output, it will also reflect back in here. So the last part of our simulation model here is the calculation event. Basically, this calculation event will just show the output voltage if there's any on the output terminal of the op-amp. Basically, it's the output because we actually declared the constant in here. If you remember the fourth constant, the output voltage, that's the one that being utilized on this particular section, the calculation event. So there you go, guys. We are already completed, writing, we created a simulation model for an op-amp. That's how easy to create a simulation model in Flux. And just to make sure that we wrote something correct in here based on the behavior of a normal operational amplifier, we need to go back to the previous circuit, which is like the inverting amplifier. And as you can see, we are now seeing something on the resistor number 2. Let me just refresh this circuit just to make sure that we are getting the latest output based from the code or the simulation updates that we have made in here. So as you can see here, the input voltage of the sine wave is 5 volts peak. As you can see here, 5 volts peak, and it's also being shown here on the output on the anode. And as you can see, the output on the R2 on the P2 terminal, which is connected to the output of the op-amp, is showing something like negative 14.9 up to 14.7 volts. So as you can see, the opamp is working. It's amplifying the input signal. I think the gain is like something like 10,000 K. I mean 100,000. So if we change this property, because we wrote a simulation model that is flexible, now we can actually control the behavior of this operation amplifier or the basic values of it just by changing the property here. So let me just change this gain to maybe like 10K, and then as you can see, the output changes to something that corresponds to that gain that we have set. So there you go, guys. We have covered an introduction to the simulator, simulation outputs, as well as we wrote a simulation model for an operational amplifier. Again, I'm Jarwin. Thank you.